Aloha. In this video, we're going to be talking about cryptographic hash functions. So I want you to open up your text to Chapter 3, Section 7, and we'll go ahead and take a look. So what is a cryptographic hash function? Well, a hash function is it's a function that's going to take a variable length message. Variable length meaning it just can be any size. So we're going to take this variable length string message, and we're going to apply some kind of a function to it. And that function is going to it's going to result in a message digest. It's basically, it'll come up with some uh, text of a certain size, and that size is fixed. It's always going to be the same size. So if you take 20 pages of text and you apply hash to it, it's going to come up with a certain size. And for example, they talk about MD5. It maps a message to a 128-bit hash, so you'll have a 128-bit result there. So if you take a 20-page paper and you apply that to it, it's going to come up with 128 bits. If you take one letter, the letter K, and you apply it to it, it's going to come up with another hash that's 128 bits. So this thing that it comes up with, that 128 bit, we call it a hash, we call it a message digest. So the terms to remember here is this is a hash function. It takes a message and it comes out with a message digest or hash. And these message digest or hashes, they are of equal length, no matter what the input is. So a cryptographic hash function has many applications in information security, including digital signatures and the message authentication code MAC, which we'll talk about at a different point in a later video. So if you look over here, you're going to see that given large message, it comes out with a simple hash right here. But when we go and we look at a shorter message, it's going to result with a hash that's equal size. And then when we run it again on just the word cold, you'll see that it comes out with another random hash here. So when we look down, you can go through some of these questions. So we need to talk about the properties of cryptographic hash functions because this is really important. What makes this effective? Well, it's going to come down to three main properties here. One is collision resistance, the other is preimage resistance, and the other is second preimage resistance. So when we're talking about collision resistance, what we mean is that we don't want any two inputs to result in the same digest. Okay, so finding two different inputs would be computationally infeasible, meaning that it's darn near impossible to do. Uh, so the other thing is preimage resistance, and that means that we don't want to be able to find the original message from a message digest. We want it to be so difficult that it's not feasible to actually try to retrieve that original message. So this property is also called a one-way property, meaning that when we go from one to the other, it's one way. You can't reverse it. And the last thing we're going to talk about is second preimage resistance. And that's similar to collision resistance, but a little bit different. So the second preimage resistance, that's going to be finding a second input that has the same digest as any other specified input. It means that that's going to be computationally infeasible. So another important property in here is called the avalanche effect. And that simply means that when you change the slightest thing in your message, it's going to come out with a big difference in the text that comes or the hash that comes out. So just changing a little bit will result in a lot. So it's the idea that in an avalanche, the slightest little thing causes massive change below it. So that's the avalanche effect. So go ahead, mix match, play around with this. And then we're talking about collision attacks. So collision attacks are basically when you're trying to find two different messages that will result in the same digest. So it's based on something, well, there's the one called the birthday attack. So birthday attack, it's based on the idea, I'm not sure if you've heard of this, but there's a paradox that says that in a room of just 23 people, there's a 50% chance that two people in that room share a birthday. So what they do is they create two groups of messages and try to see if they can get the one of them to match the hash of something from the second group. So the idea is that if you wanted to, let's say, make it look like something is secure, and you want to add a little bit to it, you just make little tweaks to something that you've corrupted until the hash of it matches the original. So that's what a collision attack is going to be, trying to essentially get the same hash function result. So anyway, that is the lesson today. It's a real short one here. We're just talking about cryptographic hash functions again. Remember your terms. Remember that you're taking a message, you're turning it into a message digest or a hash. The idea is that the hashes all come out the same size. And then we've got the properties of collision resistance, which means we don't want two inputs to come out to the same thing. We've got preimage resistance, that means we can't reverse the process. And then we've got the second preimage resistance, that means it's finding a second input that matches the same digest as another one is going to be computationally infeasible, hard. Then we've got the avalanche effect, which is just that small changes equal great changes. So a little change to the message is going to be a massive change to the resulting hash that you have. And then the last thing is the collision attack, and that's just trying to find two different inputs that'll come out with the same output. And you can use that to try to pass off something that you've corrupted as being legitimate. And that's it. If you have any questions, feel free to reach out. I'm happy to discuss any of the material with you. So have a great day, and I'll see you in the next video. Aloha.